A very good evening to one and all. Myself, Dr. P. Agilamudan, Professor of Chemical Engineering Department from Erode Sengundar Engineering College. Today I am going to discuss about the hydro power energy. The contents of this presentation is low, medium and high head plants, powerhouse components, hydel schemes. Introduction. In this, hydroelectric power systems convert the kinetic energy in flowing water into electrical energy. Falling or flowing water turns a propeller or a turbine. The turbine turns a metal shaft in an electric generator which produces electricity. That is, the turbine is combined with the generator that produces the electricity. So this is the schematic view of a hydro power plant. We can see the dam, and below the dam there is a sluice gates. When we open these sluice gates, the water flow below the dam and it goes through the turbine. That is, it rotates the turbine. The turbine is combined with the generator that generates power. That power is distributed to the various requirements. Advantages of this hydroelectric power plant is no fuel is required, no pollution, can easily work during high peak daily loads, and it prevents floods. The disadvantages of the hydroelectric power plant is it disrupts the aquatic ecosystems. Disruption of surrounding areas requires large areas and large scale human displacement. In most of the dams that evacuated thousands of people, and it lost so many forests. That is the major disadvantage of this hydroelectric power plant. How a hydroelectric power system works? The flowing water is directed at a turbine. This rotates the turbine, converts the water's kinetic energy into mechanical energy. So the mechanical energy produced by the turbine is converted into electrical energy using a turbine generator. Inside the generator, the shaft of the turbine spins a magnet inside coils of copper wire. It's a fact of nature that moving a magnet near a conductor causes electric current. So this is the another type of hydroelectric power plant. So the water is redirected from the dam and it is passed over a turbine that rotates the shaft. That shaft is combined with the generator. So the generator produces the power. Hydel scheme. There are several types. The first one is runoff plants without poundage. That is, this type of plant does not store water. The plant uses only the water which is flowing in the river. Runoff plants with poundage. Poundage permits storage of water during the off-peak period and use of this water during peak periods. That is, whenever the electricity is needed, the water will be released from the storage area, that is the dam. So that will passes through the turbine that generates the electricity. The third one is the reservoir plants. A reservoir plant is that which has a reservoir of such size as to permit carrying over storage from wet season to the next dry season. The fourth one is low head plants. In this case, small dam is built across the river to provide necessary head. That is, the height of the storage of water will be increased by the dam. So that will give more kinetic energy to the flowing water to rotate the turbine. So in such plants, Francis type of turbines are used. Medium head plants. The forebay provided at the beginning of penstock serves as water reservoir for such plants. In these plants, water is generally carried out in open canals from the reservoir to the forebay and then to the penstock. High head plant. This plant works above 500 meters, and for this purpose Pelton wheel turbines are commonly used. In this plant, water is carried from the main reservoir by a tunnel up to surge tank and then from the surge tank to the powerhouse in penstock in order to increase the kinetic energy of the water. So that's why the water is transferred from the tank surge tank to the powerhouse in penstock. Base load plants. These plants are mainly depending on the nature of load. If demand is more, these plants are used regularly and the load factor of these plants are high. The next one is peak load plants. These plants are mainly used during the peak load. Runoff river plants with poundage can be used as peak load plants. Reservoir plants with enough storage behind the dam can be used either as base load or as peak load plants as required. The ninth one is pumped storage plants. These plants are used when quantity of water available for generation is insufficient. If it is possible to pond at headwater and tailwater locations, after passing through the turbine is stored in the tail race pond from where it may be pumped back to the headwater pond. Low head plants. In this case, a small dam is built across the river to provide the necessary head. The excess water is allowed to flow over the dam itself. Francis propeller or Kaplan type of turbines are used. No surge tank is required. These are constructed where the water head is available less than 30 meters, approximately 100 feet height. The production of electricity will be less due to low head because the kinetic energy of the water will be less compared to the high head tanks. So this is a schematic diagram of a low head plant. So this low head dam increases the height of the water. So while it is opening, the water flows into the powerhouse with low kinetic energy. Medium head plants, mainly 4 bay provided before the penstock, acts as water reservoir for medium head plants. In these plants, mainly water is carried through main reservoir to 4 bay and then to the penstock. The 4 bay acts as surge tank for these plants. The turbines used will be Francis type of the steel encased variety. So this is the medium head plant diagram. So we can observe that how the head of the reservoir is increased, and we can see the penstock direction and powerhouse. High head plants. In these plants, pressure tunnel is provided before the surge tank, which in turn connected to the penstock. A pressure tunnel is taken off from the reservoir and water brought to the valve house at the start of the penstocks. The penstocks are huge steel pipes which take large quantity of water from the valve house to the powerhouse. The valve house contains main sluice gates and in addition automatic isolating valves which come into operation when the penstock bursts, cutting further supply of water. Surge tank is an open tank and is built just in between the beginning of the penstocks and the valve house. In absence of surge tank, the water hammer can damage the fixed gates. In majority of dams, sluice gates are provided. The sluice gates are opened when dam level is below level and there is shortage water for irrigation. Normally, the high head plants are 500 meters above, and for heads above 500 meters, Pelton wheels are used. So this is the schematic diagram of high head plants. So the water is first stored in the surge tank and it is directed to the penstock. From there it is sent to the powerhouse. The purpose is to give a constant kinetic energy to the turbine. When the water is stored in the surge tank and the level is maintained, the proper kinetic energy will be given to the turbine. Components of Hydel scheme. They are forebay, intake structure, penstocks, surge tanks, turbines, powerhouse, draft tube, tail race. So this is the one more schematic diagram of this hydroelectric power plant. So the construction is, we can witness the construction of a dam like structure and the reservoir, how the water is redirected into the penstock, and how the turbine rotates, and how the water is released into the river. Forebay. Enlarged body of water provided in front of penstock, provided in case of runoff river plants and storage plants. Main function to store water which is rejected by plant. Powerhouse located close to dam. Penstock directly take water from reservoir. Reservoir act as forebay. So this diagram little bit explain more about the intake wear and settling basin, channel, forebay tank, penstock, powerhouse, and again the water is sent to the normal river. This is the intake structure. Water conveyed from forebay to penstocks through intake structures. Main components are trash rack and gate. Trash rack prevent entry of debris. Penstocks. Open or closed conduits which carry water to the turbines. Made of reinforced concrete or steel. Concrete penstocks are suitable for low heads less than 30 meters. Steel penstocks are designed for any head, that is for low head as well as for the high heads. Thickness of penstocks increases with head or water pressure. Penstock gates are fixed to initial of penstocks, and flow of water is controlled by operating penstock gates, either buried in ground or kept exposed. Surge tank. Additional storage for near to turbine, usually provided in high head plants. Located near the beginning of the penstock. As load on the turbine decreases or during load rejection by the turbine, the surge tank provides space for holding water. Surge tank overcomes the abnormal pressure in the conduit when load on the turbine falls and acts as a reservoir during increase of load as shown in the diagram. Turbines. Turbines are used to convert the energy of falling water into mechanical energy. Water turbine is a rotary engine that takes energy from moving water. Flowing water is directed onto the tape blades of a turbine runner, creating a force on the blades. Since the runner is spinning, the force acts through a distance. In this way, energy is transferred from water flow to the turbine. The principal types of turbines are impulse turbine, reaction turbine. Impulse turbine mainly used in high heat plants. The entire pressure of water is converted into kinetic energy in a nozzle, and the velocity of the jet drives the blades of turbine. The nozzle consists of a needle, and the quantity of water jet falling on the turbine is controlled. This needle placed in the tip of the nozzle. If the load on the turbine decreases, the governor pushes the needle into the nozzle, thereby reducing the quantity of water striking the turbine. Examples of the impulse turbine are Pelton wheel, Turgo, Michael Banki. It is already known as cross flow or Osberger turbine. This is the Pelton turbine. Next one is, we are going to see about the reaction turbines. These are for mainly low and medium head plants. In reaction turbine, the water enters the runner partly with the pressure energy and partly with velocity head. Most water turbines in use are reaction turbines and are used in low, that is less than 30 meters, and medium 98 to 984 feet head applications. In reaction turbine, pressure drop occurs in both fixed and moving blades. In this turbine, the runner blades changed with respect to guide van opening. As the sudden decrease of load takes place, the guide vane limit decreases according to the runner blade closes. Examples: Francis turbine and Kaplan turbine. So this is the real pictures of Francis turbine and Kaplan turbine. Draft tube. It's a pipe or passage of gradually increasing cross-sectional area which connect to the exit to tail race. It reduces high velocity of water discharged by the turbine. Draft tube permits turbines to be installed at a higher level than the tail race level, which help the maintenance and repair of turbines. So this is the penstock and the draft tube, how it is designed. We can see the design of the penstock and draft tube. Power hose contains the electromechanical equipment, that is turbine, generator, excitation system, main inlet valves, transformers, switchyard, DC systems, governor, bus duct, step up transformers, step down transformers, high voltage switch gears, control metering for protection of systems. Tail race. Tail race tunnel or channel are provided to direct the used water coming out of draft tube back to the river. Important criteria of designing the tail race is kind of draft tube, the gross head and geographical situation of the area. Tail race is designed in such a way that water hammer is minimizes when water leaves the draft tube. We can see from this schematic diagram. Next we are going to see about the power generation. The amount of electricity that can be generated by a hydro power plant depends on two factors. One is flow rate, the quantity of water flowing in a given time. Head, the height from which the water falls. The greater the flow on head, the more electricity produced. Flow rate is equal to the quantity of water flowing. Head is equal to height from which water falls. A standard equation for calculating energy production. Power is equal to head into flow into efficiency divided by 11.8. The power is in kilowatts. Head is distance of the waterfalls that can be measured in feet or meters. Flow, the amount of water flowing measured in cubic feet per second. Efficiency, how well the turbine and generator convert the power of falling water into electricity. This can range from 60% for older, poorly maintained hydro plants to 90% for newer, well-maintained plants. 11.8 is equal to index that converts units of feet and seconds into kilowatts. Let's see how much power can be generated by the power plant. If the dam is in 357 feet high, the distance the water falls is 235 feet. Typically the flow rate is 2200 CFS. Let's say the turbine and generator are 80%. So the power is equal to head into flow into efficiency divided by 11.8. Here the head is 235 feet. The typical flow rate is 2200 CFS and the efficiency is 80% divided by 11.8. That gives 35,051 kilowatts power. Thank you.